Okay, so we're back. You know, I've already done the conversions, and the next part of my lecture talks about unit conversions. But when we were talking about the size and scale of the universe, we did unit conversions. And so a lot of the times we'll do examples in class, and I can't, of course, do those examples with you now. But those unit conversions, um, let's just look at the metric system, for instance, to make it easy. If we have 1 kilometer, and that 1 kilometer equals 1,000 meters, you can divide 1 kilometer by 1,000 meters, and you have 1. So that means that you could invert 1, and you could put the 1,000 meters on top and the 1 kilometer on the bottom. Each of these things are equivalent. The only problem is if you don't do it correctly, you get it wrong. So if I want to convert 450 meters to kilometers, then I have to multiply 450 meters. Which one of these, do I want to do this one or do I want to do this one to get my kilometers? Well, if we were to use this, we'd be multiplying 450 by 1,000. But then I'd really have meters squared divided by kilometers, right? So I don't want that. We want to get this one here, and we want to take that and say 1 kilometer divided by 1,000 meters. Then that has this in the denominator, this in the numerator, and those two cancel, and we're left with nothing but 0.45 kilometers. Okay, so this is unit conversions, and the fact that the metric system, no matter what our unit happens to be, what length, mass, time, whatever, the metric system makes it easy. Makes easy. So that's a really easy, nice way to do it. Now, let's see. All right, let's do one. You're going to be doing this for homework, so I guess we should do one, a couple more. So let's do 45 miles per hour. And we're going to do that. We're going to convert that. We want some blank meters per second. Okay, so this is our example. Miles per hour. Okay, first of all, miles per hour. Let's deal with that. Miles per hour. What is that really? Miles per hour, you want to have that written as miles per hour. Why do you want to do that? Because now you have a numerator and a denominator to work with. Okay? So we've got our numerator, we've got our denominator. If you just try and do it like this, you have to keep track in your head which one is the numerator and which one's the denominator. A lot of people don't even think about it as having a numerator and a denominator because it's just straight up miles per hour. Everybody just doesn't even think that of the per part of it, right? They just go, oh, that's just miles per hour. Okay, well, anyway, we're going to think of it as miles per hour, and I recommend that you do the same, especially on tests or in homework. Miles per hour. So now we can do our conversion. Let's erase that. And we need to know a few things, right? How many miles in a kilometer, for instance, or vice versa. So let's come over here and write 1.6 kilometers per 1 mile. Okay, what's another conversion that we might want to know? We want to know how many seconds, 3,600 seconds per 1 hour, right? Because we're looking for seconds here, and we've got hours here. So so we want to know that. We want to know that. Let's put a little, they're not equal to each other. How many meters in 1 kilometer? Well, we've already done that one. 1 kilometer has 1,000 meters. So these are the ones. 1 equals all those things, and we can multiply this by 1, and we can start getting the right answers. Okay, so let's multiply 1.6 kilometers per mile. So that's good. And we want to go from kilometers to meters, so let's multiply 1,000 meters divided by 1 kilometer. And we want to change hours to seconds, but we need hours to be on top, so we'll put 1 hour. So we're just inverting this one. 1 hour divided by 3,600 seconds. So that'll leave us with, we'll cancel this, cancel that, cancel this, cancel that, cancel our hour. We're left with nothing but meters and seconds, and that's exactly what we want, okay? So 45 times 1.6 times 1,000, all divided by 3,600. The units on that, let's keep the units right. That's meters. Come on, meters per second. So if we go through and plug in all those things, we should get that 45 miles per hour is approximately 20.8 meters per second. Okay, great. And how do you want to? Let me just right off the bat here. Let me start by saying, this is how you want your answer to be done. You want to say 20.8 meters per second equals 45. Now I would write it like this: miles per hour. And you put a box around it. Okay, so that's your answer. When you go to give me an answer on a test or whatever, you need to have this equal sign. You need to have what this part is and what this part is, and that they're equal to each other. Okay, so it could be E equals something, like our energy equals something, but it doesn't matter. This equals this, and then you box it in, because that's your answer. Okay, so let's do another example. We've got 1 football field. All right. We want to know how many centimeters that is. So equals blank centimeters. All right. So that's something that I'm going to ask you to do. Before I do, I'm going to give you a few things. We've got 1,000 yards in a football field equals 1 football field. We've got 1 yard equals 3 feet. We've got 1 foot equals 12 inches. we've got 2.54 inches equals 1 centimeter. What? No. What? No. 2.54 centimeters equals 1 inch. That's more like it. So now I can ask you this question. Go ahead and pause for a second and figure that out, and we'll have an answer when you come back. Okay, so you're back. What are we going to do? We're going to say 1 football field. We're going to multiply that by 100 yards. We're going to divide that by 1 football field. We're going to multiply that by 3 feet. We're going to divide that by 1 yard. We're going to multiply that by 12 inches. And we're going to divide that by 1 foot. And now we can say, oh, well, but you know what? I've got 2.54 centimeters per inch. Let's just do inch right there, and there we go. And so let's just real quick, before we throw an equal sign in there, make sure that we've got all of our ducks lined up. I think that does it. Oh, got rid of the football field. And we're left with centimeters. Okay, so good. So now we can do all of that. So we're going to multiply 100 times 3 times 12 times 2.54. And we will get 9,144 centimeters. So instead of the last yard, right, you could say, oh, no, it's the last X amount of centimeters. I don't know. If you're a nerd, all 9 yards. Okay. All right, so good. Let's do some dimensional analysis. Well, this is a good way to check your answers and to make sure that you're actually doing something that is worthwhile instead of wasting or spinning your wheels, wasting your time. I almost wrote differential analysis. That's not what we're talking about. We're talking about dimensional analysis. Okay, they call it dimensional analysis. Do they mean 1-dimensional, 2-dimensional, 3-dimensional? No, they don't. They mean meters or length, mass, and time. Okay? So let's take momentum. We talked about momentum earlier. Momentum is our mass times our velocity. And instead of velocity, let's say that it's really length per time. So we've got our mass times length per time. Okay? And this way we can say, oh, are my meters, are my units consistent? And if I have an equation that says our momentum squared divided by the mass, let's do P equals mv. Our momentum squared divided by the mass is equal to, if this is mv, then I'm going to have mass squared v squared, and I'm going to divide that by a mass. Is this true? Well, I now have how do I want to do this? I've got my mass length squared, mass squared, length squared, time squared divided by mass. That's going to give me mass, because one of these cancels out one of those. So I'm left with mass length squared over time squared. Okay, what you guys don't know is this is energy. Okay, and energy is a Newton meter, which is a kilogram meter squared per second squared. And so that's really mass. It's unfortunate that mass is also a meter, so the two m's are messing us up, but mass times length squared times time squared. Okay, so if this is energy, and that means this is energy, are these equal? Yes. So we have said that yes, this is an energy. Okay, so it's dimensional analysis. They call it dimensional analysis, but what you're really doing is saying, do I have the right number of lengths? Do I have the right number of masses? And do I have the right number of times in my equation? And when I get my answer, do I have those same things? So it'll check your algebra for you. If you've done your algebra wrong, you will not have those done correctly. So that is dimensional analysis. We can get more into that later as we're doing problems, and we'll do more examples in the future. We'll see dimensional analysis more. Okay, so now we're up to significant figures. Significant figures. All right, this is 1.6, by the way, section. To get to significant figures, we first kind of have to do a little bit on accuracy versus precision. So accuracy. Now what we're talking about is how accurate is our measurement. So accuracy in a measurement. Okay, so how accurate is our measurement? In order to have accuracy and how accurate it is, well, you kind of have to have a target, right? So here's our goal. If it's accurate, it'll be in this range, and not so accurate in this range, and then just completely out in left field would be like out here, right? So how accurate are we? So if we have a range right here, this inner spot here, if that is what we expect to be our value, that is our expected value. Okay, so you have to have an expected value if you're going to have accuracy. So I'm going to hit, let's say I have this data point, and we'll do in blue this data point, which is just right on, and this data point here. I'm pretty accurate, frankly, because on average, I'm right in the heart of it, okay? So my expected value and my accuracy is done well, okay? So that is how close is a measurement to the accepted or expected theoretically calculated value. Okay, so how close is it? That is our accuracy. So the more close it is, the more accurate. The less close it is, the less accurate. Okay, what about precision? We can be precise, we could be imprecise, right? But is our precision compared to an expected value? No, it is not. We have measurements. Let's say we do 5 measurements. And our 5 measurements, we're going to do 2 sets. Here's our first set, here's our second set. Our first measurement is here, second here, third here, fourth here, and fifth here. Okay? This is our grouping. All right? Now our second way of doing this measurement, totally different procedure, maybe different apparatus, all different kinds of things happening, and we end up with these measurements. Okay? So, which one of these 2 ways of measuring this are more precise? Well, this one has a closer grouping together. It seems to be more precise. Now we could redo our target up above, and we could look at a green set, which is here like this, okay? Or we could look at the blue set and say, that, right? The blue set is by far more precise, right? However, if you were to average out the green set might average to here, okay? And we know that this blue set does not average to be that good. So the green set is maybe more accurate. The blue set is less accurate, but more precise, okay? And so that is the difference between accuracy and precision. Basically, right there. So here we are more accurate, here we are more precise. Green more accurate, blue more precise. Okay, so what does that have to do with uncertainty? All right, I'm going to leave that little picture right there. Let's do uncertainty. So we want to measure the gravitational constant G, okay? And G is well known. Everybody knows G. It's been done 1,000 times by very serious people. And G is 9.8 meters per second squared. Okay, that's the accepted value. We're going to go with that. And in fact, every time you do an equation the rest of the semester, this is the value of G that you want to use. Okay? But let's say we do 10 measurements. 10 measurements. All right, we've got our 10 measurements. The values range from 9.7 meters per second squared up to 9.92 meters per second squared. So that's our range. Now we can average that out, and we average out to be 9.81. That's right in the middle, meters per second squared. So this is our G average. Okay. Fine. Let's do a little number line here. Here's our 9.92. Here's our 9.70, and right down the middle of it is 9.81. From here to here is 0.11. From here to here is also 0.11. However, we're taking our average and we're subtracting 0.11 from there, and we're adding to there. So what would we say? We've done all these measurements. Our G is going to equal our G average plus or minus our delta G. Our delta G is this distance. Okay? Oh, I wrote delta like that, and here I really want to write it like this, because when we're dealing with statistics, this is our uncertainty. Okay, this thing is our uncertainty. So 0.11 would be our uncertainty in this case. So this is how we would report it. So we would say, okay, we would write our paper up, and we'd say this is our 9.81 plus or minus 0.11. And then, of course, you want to have meters per second squared. You got to have your units in there, and we would box that in and so forth. That is our measurement theoretical experimental value. Okay, RGEXP. All right. Discrepancy. So what did we just do? Let's get back to what we just did. This is our precision. And this is our average value from measurement, from experiment, or our measurement. Okay? All right. So now we want to deal with discrepancy. So we know G is going to be equal to 9.8, right? Meters per second. In fact, you know what? I'm gonna do you guys a solid, and I'm gonna write out. It's really 9.80665 meters per second squared, and we want to know what this is the accepted value. Okay, this is the scientific. All the experiments done so far have given us this value on Earth. Okay, what is our discrepancy? Our discrepancy would be our 9.80665 minus 9.81, and then we want to take the absolute value of this, right? and that is going to give us our discrepancy. What is our discrepancy here? I haven't. 9.80665. I'm going to subtract off 9.81, and that gives us the absolute value of that is 0.00335. Okay, so that's our discrepancy. And of course, we want to keep the units, meters per second squared. But discrepancy refers to what? A comparison between the expected value and our value. Okay, so the difference in that gives us an accuracy, right? So discrepancy relates to our accuracy. The larger the discrepancy, the less accurate we are. Okay, so that's our discrepancy. Now, one thing that people like to know regarding precision in your measurement, and one thing that I often want to know when you do your lab reports is what is the ratio? Let's do it a different way. Let's say percent uncertainty So what is your percent uncertainty? Well, you have an average. You've measured your average, but you also have your uncertainty. So you take your uncertainty. Why do I keep writing it as a Q? I don't know. And we're going to divide by our G, and then we're going to multiply that by 100%, right? And that's going to give us our percent uncertainty. So in our case, let's go back up a little bit, get our numbers. Yes, 9.81 and then 0.11. So we can say 0.11. We're going to divide that by 9.81. We're going to multiply that by our 100%. And what do I have? 1.1% uncertainty. Okay, so this is very often, in fact, quite often, just about every time I want to know what your percent uncertainty is. Pretty much every time. You may as well just do that every single time. What about your percent discrepancy? What does that relate to? That relates to the accuracy. How accurate were you? So my percent discrepancy would then be whatever the accepted value of G is minus our mean value of G divided by the expected value, accepted or expected value times 100%. So we have 9.80665. Now, of course, you want to do this, right? Because you want a positive thing, absolute value. And we're going to do our 9.81. Then we're going to come down here and divide by 9.80665. We want the absolute value of that. We're going to multiply by 100 to get that percentage. Let's give ourselves some room. And this would be our percent discrepancy. Yet again, I need to, I've already done this. That is 0.00335. So I've already done that. Now I'm going to divide by 9.80665, divide. And then I'm going to multiply by 100. And that's going to give us our percent discrepancy is equal to 3.4. I'm going to round up to 3.42 times 10 to the minus 2%. So we are not far off at all. Very, very close with our 9.81 measurement. Okay, so good for us. Excellent job by us, right? Okay, so let's move to Chapter 2.1. Scalars and vectors. So this is where I always do the joke. What's the difference between a mosquito and a mountain climber? And everybody's like, well, there's all kinds of differences. Or how are they the same? I don't know. I'm pretty good at jokes usually. Anyway, I think I might be getting this one kind of mixed up. But anyway, mountain climber and a vector. One is a scalar and one is a vector. A vector, the mosquito's a vector for malaria. Biological vector, they call it. A way you can get all right, if I'm not going into the joke any further, that's it. It's a good joke. At least it's terrible. It's a good dad joke. We can multiply scalars. So no. I'm not going to get into that bit just yet. Let's not talk about what we can or cannot do with these scalars and vectors. Let's talk about what a scalar is. And the best thing to look at is velocity, which is how fast you're going, and speed, which is how fast you're going. So why are there two words for velocity and speed? All right, well, first, velocity is the vector. And I like this example because it's got V for vector, right? So velocity is your vector. Speed is your scalar. All right, so far so good. Now, what does that mean for us? That means velocity has not just the number of the quantitative number for the speed, but it also has the direction. So you're doing 75 miles an hour. Well, that's just your number. And it doesn't matter which way you're going. But if you're doing 75 miles an hour due west, then you have a velocity. Okay? Your velocity is in the westerly direction. if you just have a speed, that's just your speed. So a vector has a direction, so it has a magnitude that's your number, okay? Both have a magnitude. But the vector also has a direction. So magnitude and direction. Here, scalars, just a magnitude. Well, scalars are a lot easier to work with, right? Everybody would rather work with a scalar. And when we start adding in conservation of energy to our life, things get a little bit more simple because energy is simply a magnitude or a scalar, right? So you guys will find that that is a beautiful addition to the things that we know and are able to work with. We'll get there in a little bit. We're not there yet, so let's continue on talking about scalars and vectors. Scalars. Let's address scalars first. Scalars. Scalars we can multiply. So let's say we have alpha and we're multiplying times beta. That gives us gamma. And we can also multiply vectors. And we take our vector. A vector has a little arrow over the top of it. And I'm going to say instead of C, I'm going to call it our resulting vector. Okay? Now, when we do this, we get no direction. So we have now converted two vectors. This is a vector, not a vector. We have now converted two vectors into a scalar. Okay, we've multiplied them together. That gives us a scalar. Some people might know what this is called. This is called the dot product. And the cross product we'll show later maintains a vector. Okay, so you can multiply two vectors together and do in the cross product and end up with a vector. Okay, you get a magnitude and a direction. However, we're just going to be doing this for a little while until we actually need cross products. Okay, so we're doing the dot product for now, and we will add the cross product in later. This is part of the jumbling of all the chapter sections and whatnot. We can also take a vector. Let's take our vector b and say that that vector b is equal to a scalar times our vector a. So in this situation, we are multiplying a scalar and a vector. That's our scalar. That's our vector. And we are getting another vector out of it, okay? But that vector has to have some things. B must be parallel or anti-parallel. That's anti-parallel, like this. And this is just straight up parallel, okay? This means one's pointing in one direction, one's pointing in the other direction for anti-parallel. These guys are just pointing in the same direction. But B must be one of those two things because there's no direction being added by this scalar. So the direction all comes from this A. So B must be parallel or anti-parallel to the vector A. These are good symbols to know. There's also perpendicular. Okay, so this means perpendicular. So we've got parallel, anti-parallel, and perpendicular. Okay, all right. Now, we could do another thing, and we could take the absolute value of these things. When we do that, all of these things are scalars. Because the absolute value of something doesn't care about what direction it's going in. Okay, so we have stripped the direction, and all of those things are now scalars. Okay, so good. Let's do a example. So our example is in one dimension. And you might want to look at see figure 2.7 in your book. And we're going to be dealing with meters as our units. So that's our units, all meters. And we're going to do B equals alpha times A. And here we've got A pointing in that direction. We're going to multiply that by alpha, which is some number. And that's going to give us equal to B. And B is represented like so. Okay, so alpha times A equals B. If we put some numbers in here, we've got plus 1.2 times 3, and that's going to equal our plus 3.6. So here we are pointing in the positive direction. Now I'm going to give some coordinates here. This is plus, this is minus, and we can put 0 right in the middle. Okay, so to the left is negative, to the right is positive. So this is a positive, A is a positive vector, B is a positive vector. And it shows mathematically that we are correct. Okay, now we could make alpha equal to minus 3. Then we have 1.2 in the positive direction. We're going to multiply by minus 3, and that's going to give us a negative 3.6, right? So our B now is going in this direction. Okay? So this purely signifies the direction of B. The magnitude of B stays the same. If we take the magnitude of B, that's equal to 3.6. Well, up here, the magnitude is also 3.6. So magnitude stays the same. The direction is what changed, and it all changed because alpha was now negative 3 instead of positive 3. Okay. Let's do a little vector addition. Vector addition. And I know these things seem very simple, but it's definitely, this vector stuff is on a test. When we start getting into the trigonometry of the situation, that's going to make it a little more complicated, but we definitely need to know how to add and subtract vectors. Okay, so let's do addition. We're going to add these two guys. Where did my R go? That's our resultant. Okay, so we can do a couple of things. We can say first our A is still our 1.2 to the right. So it's plus 1.2. We can say that our B is 1.5 to the right. And we want to do A plus B. Okay, so A plus B, if we were to add those, so what I'm going to do is I'm going to pick B up, I'm going to add it head to tail, to A, and that's going to equal a vector this long, and that vector is 2.7, right? Because 1.2 plus 1.5 equals 2.7, and that is our R vector. Now, if I were to do this really correctly, I can't get it perfect, right? But if I were to do it perfectly or close to perfect as I can possibly do, I would have both of those vectors from here to here be the same length. Okay, so mathematically those are the same length. All right, in your imagination, please make those the same length. Now what about, I want to do A plus, no, I want to do A minus B. And that is going to equal R2. Okay? A minus B. Well, what are we doing when we say A minus B? We already know what B is. So if we want A minus B, we could really say that that's A plus minus B. Well, what is minus B? That's just B multiplied by -1, right? So what happens when we multiply by -1? We saw it earlier. When we put that negative sign in, oh boy. When we put that negative sign in, it gives us the negative on the other side. So if we have B and we multiply by -1, we're going to end up with B but pointing in the other direction. So we can do that. We can show our A going 1.2 this direction. And we've got our B going 1.5 in that direction, our negative B, okay? We pick them up, we put them down, head to tail. So I'll rewrite A here. I'm going to do it head to tail, so I'm going to pick up B and place it down right there on top of A. We started here, we ended here, and our net vector is here. So this is our 2. So we've got our A, we've subtracted B, and we're left with R2. So what is R2? R2 equals -0.3. If we want the absolute value of R2, we say it's 0.3 because we don't care about the direction anymore. We only care about its distance. So subtraction is simply the addition of the anti-parallel vector, right? So we're just taking that and making it negative, and you pick it up, you put it down head to tail. I am going to continue. We need a third. So we're going to stop here, and we're going to continue on with our next bit. So take a break, come back, and we'll keep going.